A good time. So, this is part of the research we're doing in regards to wireless communications. I'm Rick Roberts from Intel Labs, and I'm with the Wireless Communications. Hey, glad to meet you. A couple of years ago, we started looking at wireless communications in regards to what you do with LEDs for communications. LEDs actually have a modulation bandwidth that you can turn on and off very quickly, so they can send data. Initial research was actually looking at sending data to with the LEDs, but in the process of doing that, we came up to the realization that we had another usage here that we thought would be very interesting to the automotive industry, and that is what we call visible light positioning. And basically what it is using the tail lights on a car, for example, with receiving sensors embedded in the front end of the car that can see these tail lights, using that information for this automobile here to determine its relative position with respect to this car here. So it can determine the two-dimensional XY position with a high degree of accuracy.
This scheme that you're thinking of, do these tail lights have to be modulated?
Yes. Yes, they are. They're actually over here. So let me show you here. This is a red LED that we just brought off the shelf from an electronics supply firm. It's actually not on steady. It's blinking 20 million times a second. Okay. There's just a little high precision oscillator in here and a small driver that blinks that light. That blinking light is observed on the photodetectors over here. And if I looked at the output of the photodetectors, what I actually would see is that 20 megahertz waveform. If I compared those two waveforms, I would see that they're slightly time skewed. There's a phase shift between the two waveforms. And by measuring that phase shift, we can translate that into time difference of arrival. And once we have that information, we can determine the position of this box based upon the geometry of the problem.
Like thing with echolocation, except for much higher frequency.
It operates on the same principle as GPS. GPS sends ranging signals and you process them. And then by having two tail lights instead of just one, that's how we can do the XY positioning. To illustrate how accurate this technique is, what I'm going to do is I'm going to set this to roughly 16 inches on the yardstick. And if you look over there, you can see it says 16.1 inches. So in this particular setup, we generally run better than a quarter-inch accuracy. Yeah, and what we're showing here in this a simplistic use case of a tailgate warning indication where you can be in the red zone, or you can move through the yellow zone into the green zone. Just a simplistic, illustrate what you could do. Now, in the case of if we have multiple lanes of traffic, and one might ask, well, won't that be a confusion for your sensors to process? And the answer is not really, because what we would do in a real deployment is we would not have a single photo detector. Rather, we would have a lens system with an array of photo detectors behind it, much like a digital camera. And much like a digital camera, it had no trouble seeing the multiple light sources. We have no trouble seeing the light sources, which show up as modulated pixels in the image array. We just have to find those pixels that are ingesting data.
Right.
So when we do that, then this allows us to actually track multiple targets. In fact, we use it almost like the military terms. We have target identification, target acquisition, target tracking. So you can keep track of the vehicles moving around you. Now, there already are deployed in cars various sensor technologies that do something similar to this. And they're very good. I mean, we're not saying rip them out and put this in. But the advantage of this is It has a high degree of precision, and it uses what is already on the car. I don't have to add anything. I don't have to add radar, or sonar, or LiDAR. I just use the LED lighting that's on the car, and the auxiliary. You have to put a modulation circuit in there. That's right. Right. The cost differential versus what you can actually gain with multiple target tracking and things like that, we think is the cost trade-off. Yeah, we're in the early discussions with the DOE about how we think this technology could fit the IntelliDrive concept. In fact, we think it's probably one of the more viable technologies in that case, especially if you wanted to set up a road train of cars that were doing a lane of traffic. One of the interesting properties of this technology is it's least accurate at long distance, and as the cars pull up to each other, the noise ratios go up, and so the accuracy just gets better and better the closer you get. That's a good question. Yeah. If your lighting is covered with snow, obviously it's not going to work. Of course, your brake lights are compromised if the lens is covered with snow. Another thing that people say is, what if it's fog or any other thing that's obscuring the vision? Yeah, the system will break. But the comment is, if it's so foggy that the system can't work, then this is using the same wavelengths your eyes need, so if you can't see, you shouldn't be out driving either. So in regards to another question that people sometimes ask is, how robust is this in regards to ambient lighting conditions, for example? Here in this room, we may know attempts to dim the room. And in fact, I can set this onto a given inch setting of 18 inches. Here it says 18.2, and I can shine my flashlight right into the lens, and as you can see, it has absolutely no impact.
Your filters on the detector.
Exactly.
Filter everything out.
Exactly. That's exactly. At the output of the detectors, we have a 20 megahertz bandpass filter that gets. As long as the detectors don't overload with the light intensity, then we stay linear, and you have linear system. In regards to why would Intel be looking at this? I mean, we don't build LED lights. We're not going to build tail lights, but this is a embedded processing opportunity for us. So we look at the whole concept of LED lighting and participating in communications in some sort, and potentially in the market. So that's why we're investing. As far as our research as where does this go, we're actually now working with the University of California and Rice University in Texas in regards to finishing up some fundamental research as to how well does it work outdoors, how far can you really get, and those kind of issues. And then in about 12 to 18 months from now, we're going to be looking at convening a workshop with a call to industry to come participate in the workshop and try to figure out where we want to take this technology. Yes.